This presentation focuses on the basic introduction to the concept of digital twin and its most essential definition. Current and everyday examples of its use are presented. In addition, methodology to obtain simpler surrogate models from a complete digital twin and their uses are also addressed here. As an involved party in the iCAREPLAST project, UPV has developed a digital twin of a pilot recycling plant, which allows a better insight and understanding of this process. This is a really interesting approach since we are moving towards a horizon in which the physical and digital worlds are closely connected. But first of all, what is a digital twin? A digital twin, as the name suggests, is a digital replica of a product, service, or process. It is, in essence, a computer program that uses real-world data to create simulations that can predict how a product or process will perform. These programs can integrate the Internet of Things and artificial intelligence. A digital twin can be a digital replica of an object in the physical world, such as an engine or wind turbines, or even whole cities. Digital twins can also be used to replicate processes in order to collect data to predict how they will perform. These virtual models have become a key element in modern engineering innovation. In short, digital twins can leverage strategic technology trends, prevent costly failures in physical objects, and, through the use of advanced analytical and predictive capabilities, test and monitor processes and services, allowing the digital version to mimic and simulate what is happening in real time, creating opportunities to gather information about performance and any potential problems. NASA was one of the first to use digital twins technology for space exploration missions, where virtual prototypes are thoroughly studied prior to the construction of a physical version to ensure its performance meets absolutely all requirements. Since then, this technology has been used in an ever-growing array of industrial applications and processes. Following this use trend, more and more sectors and industries are adopting the use of digital twins. The use of this technology is widely extended in sectors such as automotive, manufacturing, aerospace, healthcare, or even in construction and city planning, where digital twins have already been used to solve a large number of challenges. For example, a digital twin can be used to help cities become more economically, environmentally, and socially sustainable. Virtual models can guide planning decisions and offer solutions to the many complex challenges faced by modern cities. For example, real-time responses to problems can be informed by real-time information from digital twins to allow assets such as hospitals to react to a crisis. The benefits of digital twin differs depending when and where it is used. On existing products such as a jet engine, a digital twin can be used to monitor the performance and reduce maintenance burdens. Digital twins can also be used for prototyping ahead of manufacture, reducing product defects and shortening time to market. Other instances of digital twin use can include process optimization, monitoring, and simulating to improve performance. One of the main advantages of a digital twin is that it can be used with a prototype to offer feedback on the product as it is developed, or can even act as a prototype in its own right to model what could occur with a physical version when built, while reducing risk of physical accidents and unplanned costs. A digital twin design is made by gathering data in order to represent the behaviors or states of the real-world object or process and creating computational models to test it. The basis of the idea is the use of data, math, algorithms, and computer instructions to create digital representations of the real world. Despite the enormous usefulness of digital twins, there are certain applications in which the computational load and time required may result in these models being too much. In this case, the use of surrogate models can be beneficial and interesting. But what do we understand for surrogated models? Surrogate models use the data obtained from a comprehensive sensitivity analysis of a digital twin to obtain fast, static models in situations where it is not necessary to simulate the entire process. Thus, surrogate models can be understood as a simplification model for digital twins. These models can be represented as a black box, where from some inputs, the outputs of the system can be known. But first, the sensitivity analysis data must be fitted. There are a multitude of data fitting methods by which surrogated models can be generated. One of the simplest methods is polynomial fitting, where the input-output relationship is represented by a polynomial equation of the desired order. On the other hand, a more advanced and accurate method is the use of neural networks, whose complexity can vary widely, from shallow neural networks to deep neural networks of extreme complexity. The use of surrogate fitting models is very interesting in steady-state case study applications. If we take a chemical plant as an example of application, one of the most interesting uses of these models is the application of multi-objective optimization techniques to certain processes, either as a whole or divided into simple subsystems. In the iCAREPLAST project, a digital twin of Unbaser's pilot plant for plastics recycling has been designed. This digital twin has been developed using Aspen Plus software to model the pyrolysis, alkylation, or aromatization and oxycombustion processes. For this particular case, the composition of the plastics and the pressure and temperature conditions of the processes have been defined as input variables of the process. As previously mentioned, the use of the complete model may involve a high computational cost for the study of very specific cases. Therefore, surrogate models have been developed in MATLAB for each of the sub-processes. For this purpose, it is necessary to previously export the results of an extensive sensitivity analysis in Aspen in the corresponding format. MATLAB surrogate models can be schematized as black boxes, where input variables give rise to output variables. Each of these variables will be defined according to the input-output relationships to be obtained. For example, in the case of pyrolysis, the relationships between the amount of aromatic compounds, olefins and paraffins have been established as a function of the composition of input plastics and the pyrolysis temperature. Two different methods have been used to fit the surrogate models. The first is polynomial regression, where each relationship is fitted by a fifth-order polynomial. For the second method, simple shallow neural networks have been used. This second method has been used in those cases where the results obtained by polynomial fitting did not fit correctly. To conclude, digital twins are extremely powerful and useful tools, especially in the field of engineering and innovation, where they can be key in the development of future technologies, more connected, accessible, and understandable. In addition, the use of surrogate models can be a powerful addition to the use of digital twins, complementing the use of simpler parallel applications.